We are the team Gravity Fringes. Can you hear me properly? If for any reason at some point you lose connection or whatever, please just let us know and we'll repeat whatever it needs to be. So, as a recap from the pitch we gave on Friday and a summary, we have designed an exhibit where visitors can grasp the concept of gravitational waves and also learn about the only experiment that's capable of measuring them, the famous LIGO. Gravitational waves are ripples in the fabric of space-time. They stretch and contract distances as they pass by. But they're really strange. They were predicted by Einstein with his theory of relativity, but even he was really confused by them and really doubted his own discovery. On the other hand, LIGO is so complex that it took decades to build. So how can we explain all of this in a single exhibit? Well, with our proposal, the visitors will experiment with the very same concepts that scientists also play with in real-life staggering machines like LIGO. Our target audience is very wide. Prospective visitors start out at age 8, which is the starting age for the Science Gateway exhibit. And from school field trips to a family day out, or even a seasoned physicist who wants to share their excitement with their partner, we have made sure that everyone can have fun with this exhibit and learn something new. In our proposed solution on how to do this, we'll have a trampoline that represents a universe with a black hole at its center, ready to pull inward other celestial objects. In this picture, you can see that for a black hole, we have used a heavy ball, but another option we contemplate is an actual hole in the fabric, which could double as a return mechanism for other balls that the visitors throw in. Attached to the trampoline off to the side, you can see a little gravitational wave detector. It is a downscaled version of LIGO called an interferometer, as you can see there. It measures the ripples in the fabric of the universe, or this little universe in this case. You, the visitor, will be able to roll balls of different masses representing different celestial objects into orbit and see the gravitational waves they create, as well as the visual output of the interferometer, a characteristic pattern of fringes, all in real time. We have taken an old and well-known analogy, a fabric universe, to a new level.
Our hacking time has been very productive. We've been prototyping at a small scale to fit our apartment size. In the video on the left, we see a ball orbiting on a small-scale prototype of our fabric universe. The red traces show how we track the motion of the ball using a webcam. We later project a simulation of the gravitational waves. The video on the right shows how the gravitational waves change the interference pattern. The shifting of the fringes corresponds to a length change of the interferometer. We use software to measure the strength and frequency of the gravitational waves in real time. Besides no one else before us showing you a mini LIGO on the fabric universe, we've developed a series of explanations that layer 4 levels of difficulty. As you can find here, we see these layers as an iceberg of knowledge. First, you can have a nice introduction and keep going to learn more. Thirsty for more? Go to the next level and you'll dig into complexity. Last but not least, are you working at LIGO? No problem, we've got you covered too. A crucial step for our team were 2 sets of interviews. For interviews with experts from multiple backgrounds, such as theoretical physics and museum exhibition, that provided valuable feedback to make some improvements in our proposals. Also, we virtually user-tested different potential users ranging from 8 to 16 years old. It was an excellent experience to get challenged by such talented young people. So, after all these amazing conversations, we've gotten some great takeaways and things to consider in our iterations. There was a high acceptance of the concept of gravitational waves. The combination of LIGO and gravitational waves was found exciting and intuitive. Everyone believed to learn something from it. Learning by using the scientific method was a huge hit. We saw that depending on the age, they wanted more or less control over the experiment. And also, we've had the opportunity to identify some flags that we've already started to address.
And who are we? Well, we're an enthusiastic bunch. We are scientists and designers, communicators and makers. You ask, we deliver. And indeed, as you just saw, we are ready to build the full-scale prototype. The material is already waiting for us at CERN. So as soon as COVID measures will be lifted, the whole team will meet in Geneva and we will finally build the prototype. And also, of course, share a fondue and some fun all together physically, finally. The prototype will at that point be ready to be tested in schools, and modifications will be implemented based on the feedback that we will receive. But we need your support to make all of this happen. We will need access to a makerspace to build the prototype, and we will need to continue the successful collaboration with CERN, in particular with Emma Sanders and Corinne Pralavorio from the exhibitions department, who supported us in the past months and who we especially thank. Finally, we will also need feedback on our full-scale prototype. Do you want to be our first visitors? Now we are ready to answer all of your questions.
Thank you so much, Team Gravity Fringes. Good call to action. Please go ahead, judges, if you would like to ask any questions or give any comments.
Yes, I have a question. Very interesting solution for the interferometer using the webcam. However, I mean, the question I have to you is the following: where in this demonstration the concept of fusion about two very heavy bodies is shown? Clearly, you have also a mission during the acceleration in the orbit, but what really makes those the gravitational waves visible is the big signal at the very end of the process. I'm not clear to me how this is implemented there. And number two, another concept which I think would be interesting to introduce is that it's not just one interferometer which makes this result possible, but it's a network, international network of accelerometers. And the wider is the system of network of accelerometer, the better the result is. Could you comment on that?
Yes, so if I could try to answer both of your questions. I really thank you for the point of how the merging point is crucial. Something that is visible for sure at the stage at which we've built this or some of our prototype is that the object will speed up as it reaches the center, and once it falls in, it will stop. So the gravitational waves the signal will speeding up the movement of the fringes as the object falls in, and then it will disappear as soon as it has fallen in. We still have a lot of playroom to test different tensions of the fabric, different fabrics, which we've ordered already, several of them, to play with the speed of light in the fabric universe and see how we can amplify the signal to noise ratio to try to get a maximized signal as expected when the object is really close to the black hole. So this is our next thing to play with, and we will pay attention to that. Thank you. And for the network of interferometers, for now our proposal has only one. And we recognize that having at least 3 interferometers of this type on Earth allows us not just to get a better signal because you just have more data, so that always improves the signal to noise ratio in real experiments, but also to triangulate the position and know where in the sky the merging event, the orbiting of really big objects happened. And while in this prototype we don't plan to have multiple interferometers, to make the connection as straightforward as possible for the viewer, as part of the explanations that we are in the process of writing, that we've mostly written for the visitor at the different levels. For the visitor who wants to learn more, one of the blurbs that we actually have for them to read is about how there are multiple instances of experiments like LIGO across the world and how they use the data they get to triangulate the position of the source of the gravitational waves. So this is not something that we have built into the experiment in favor of preventing too much complication, but that we have aimed to address in the explanations for the visitor who's curious and wants to learn more.
Thank you.
And Kyle, I think you're muted.
Sorry. Thank you very much. Very interesting. I would like to know a bit more about how you imagine people will relate the experiment to the real world. Uh, if you could tell me a bit more about how do you think people will contextualize this concept? If I'm
So
clear.
yes, so with our interviews and the user tests that we did, we realized that like at least on a superficial level, some basics were conveyed just for the observation and the interaction with the kind of like the object. There's a further connection with more complicated ideas that needs to be developed, of course. But that's why we decided to separate kind of like the exploration from the more additional information that the user can learn at its own pace. So every person will be able to interact with the concepts as if it was the scientist, and at the same time be interested and eager to learn more with all the additional information.
Thank you.
If I may add just a really brief comment, as Carla was saying, even if the visitor doesn't read too much, or even if they don't read anything from the accompanying text, um, the people we interviewed, even the little children, had already seen this analogy of space-time as a bendy fabric. So as soon as they see the movement of orbits, they immediately thought of objects in the universe moving. So once they made that connection with the real world, which we're getting thanks to their previous conceptions, then they were really quick to jump to, oh, this is an experiment. Let me try to make predictions of what the fringes will show when I shoot balls of different masses. They made that connection, and they were really happy to identify the fabric with the real universe.